Hello, everyone. My name is Allan Jude. I'm a FreeBSD developer and an OpenZFS developer. And I also work at Clara, which is a FreeBSD professional services company, developing new features for FreeBSD and supporting FreeBSD and so on. So today, I'm going to explain to you, like you were 5 years old, how caching works in ZFS. So we'll go very, very briefly over what ZFS is, because I'm hoping most people already know and are maybe using ZFS. Raise your hand if you are actually using ZFS already. Yeah, most everybody, so that'll help things go along. Then we'll talk a little bit about what caching is in general, and then we'll get into what is special about the way ZFS does it, and how some of the other features can make a big difference there. Kind of touching on a little bit of what Benedict talked about in his talk with the compressed arc and how big of a difference that makes, especially with content like databases. So, like I said, ZFS is this magical file system that combines with the volume manager. So rather than having one tool to manage your RAID, which is making some number of hard drives look like one really big hard drive, because most file systems only understand one disk at a time. And so we had this whole layer where we'd lie about what the disk was, and it was actually multiple disks, but the file system didn't have to know that. But if the file system doesn't know what's going on under the hood, it can't help you when things go wrong. So in ZFS, where you combine the volume manager and the file system, it means that ZFS can tell that that block is on one disk and this other block is on another disk. So when it writes its metadata and it stores multiple copies, it tries to make sure they go on different disks. So if one disk fails, or even just returns corrupted data, that it can read additional copies of that block off a different disk. The other thing that's really nice about it is, previously what you would do is you'd have that use RAID to make one big virtual hard drive, and then maybe you would partition that into a number of different partitions for your operating system. And inevitably, you'd make one of them too small and one of them too big, and you would need more space on one side or the other. With ZFS, you can create as many file systems as you want. I think it's 2 to the power of 56 is the number of allowed file systems. And all of them share the available free space. So whichever file system needs it has access to that free space. Although you can use quotas to make sure that the log data set never uses more than so many of your terabytes, or what's called a reservation that says at least this much space is only usable by the database, so that no other process can starve the database for disk space. And all the data that's written, including the metadata, is checksummed, so that when ZFS reads it back, it can check and make sure that the disk hasn't scrambled it in the process of storing and retrieving it. And it has optional transparent compression, because especially if you have data that's highly compressible, if you compress it using one of the really fast algorithms like LZ4, it actually reduces latency, whereas you think compression, that's extra work that's going to make it take longer, but I'm going to save some space, so maybe that's OK. But with LZ4, because it's so fast, you end up saving time, because writing less data takes less time than writing the full amount of data, because the compression is fast enough. And it's copy and write, and you get snapshots and clones and all the fun stuff for free. And importantly, each different file system you create can be tuned separately. So you can make different file systems that are good for different things. Kind of like how /var was originally meant for all the files that were going to change all the time, but we usually just slapped it on the same disk. With ZFS, we can tune each file system individually, and we'll talk more about that at the end. Anyway. So, caching. How do computers work? As it turns out, there are multiple different tiers of storage in a computer. Some of these are persistent, and some of them are not. But they each have different characteristics. Some are faster, or have lower latency, or have a lot more capacity, or have better durability. But you end up with this hierarchy. Like we were talking about, you have your CPU L1 cache, which is very small, usually only measured in kilobytes. but is really, really fast. And you have L2, which is bigger, but still usually not more than single-digit megabytes. And then now we have L3, and that can get up into double-digit megabytes. But then we have RAM, which is really fast, and you can usually get, a couple hundred gigs if you really want to pay for it. But then we have, but all of those, if the power goes out, the data is gone. But then we get things like NVDIMMs, which is like memory, except for it actually retains its content through a power cycle. Or we use disk caches that are fast, and then we get down into slower and slower disks, and then tape, and then the cloud, and so on. So as early as the 1940s, we had this idea that we recognize the possibility that with this hierarchy of memories, each of which, as you go down, gets larger but slower, means that we can architect a system to take best advantage of that. So a cache is this idea of, if we just use some data, most likely we're going to use that data again soon. It's more likely we'll use that same data again soon than we will use some other random piece of data. And so if we keep a copy of that in one of these closer caches, it'll take us less time to go and retrieve it. But since it's just a copy, if we don't end up using it, it's safe to just throw it away. Whereas the copy on your hard drive, just because you're not using it, doesn't mean you necessarily can just throw it away. But at these faster tiers, we have less and less memory, so we have to be picky about which data we're going to keep around to get the best possible outcome. Because the faster storage is basically a precious resource because we have so little of it. So we need some kind of algorithm for deciding which data we're going to keep in these more precious, smaller caches, and which data we're going to throw away in order to get something more likely to benefit us into that cache. And so in 1965 or so, maybe even earlier, the concept of a least recently used caching algorithm came up. Because as it turns out, if you have any free memory in your computer, it'd be better to use it to keep recently used objects than to just have it free and not doing any work. So this is a basic outline of how the LRU caching algorithm works. We're going to access all these different pieces of data, piece A, then B, C, D, E, and then we're going to go back and use block D, and then F. So each of these is the cache we have as we go through each step. So in the beginning, at step 0, we have the data A, and we've put it into our cache and used it. Then we access the next block, which is B, and it goes in our cache. And beside each block, we're writing down when we used it. And instead of a big long timestamp, I've just used incrementing numbers here. So at time 0, we use block A, and at time 1, we use block B. And then we move on to the next step. At time 2, we use block C, and then at time 3, we use block D. Now our cache is full, but if we go to use A, B, C, or D again, it will be very fast because we won't have to go get it from the disk, we can get it from this cache. But instead, we actually use block E. So since there wasn't room in the cache, we have to kick somebody out in order to put this new block E in. So we find the block that has the oldest time, the block that we used least recently. And we throw it out or overwrite it with this new block E. So now we have B, C, D, and E with their access times. But the next thing we do is use block D. Lucky for us, it's in the cache, so we can access it faster. But we have to update the time on it from step 3 to step 5 so that we don't throw it away because we've actually used it, so we move it back to the front of the list. And then we use block F. Again, we're low on space, so we're going to find the block with the oldest access time and overwrite it. So that's the basics of how an LRU cache works, and that's how most of the caches in your operating system and in your hard drive and all the other things work. So the advantages to this is it's a relatively low overhead linked list data structure, and it works pretty well. And the locality principle tells us that if you visit a location in memory, you're more likely to visit that same location again than any other random location. And so keeping the data we're using the most in cache is most likely to get used again, and therefore give us the best answer. The problem with that graph we just saw is that it doesn't measure how frequently we access data, just how recently. So as our workload changes over time, it can't really adapt to that. And if you do something like, say, once a night, you do a backup, and so you go through and check every file to see if it's changed, you're just going to keep cycling through every block through that cache. And even the one block, even though you use it every 10 seconds, it might end up keep falling out of the cache because you use some other blocks more recently, even though you don't use them as frequently. You access each block once, and this one block 100,000 times, it doesn't matter. We just go by the timestamp of the last time you accessed a block. So it doesn't consider anything but the most recent history. And doing something like a backup or whatever will just completely empty the cache, basically, and is not helpful. So then, once we got into the 70s, somebody came up with the idea of a least frequently used cache. So instead of looking at the last time we accessed the data, we look at which data do we use the most. Maybe caching that will be better. So every time we access a page, we increment its hit counter, and when we're low on space, we take the object with the lowest hit counter and replace it with the new objects. Unlike least recently used cache, scanning a database or doing a table scan in your database or backing up a file system isn't going to completely invalidate this cache because you read each block only once, so it's never going to get bumped up into this cache. We're going to keep the frequently used files instead. And the infrequently accessed objects won't cycle through our cache, dislodging all the useful data that we are actually caching. So the advantages are it's immune to that scanning problem we just talked about with LRU, and it provides really good performance for that data you use a lot. Because the advanced version of the locality principle is that if we've visited this location a whole bunch of times, we're likely going to keep doing that rather than go visit some new place. But the original versions of this, especially the data structure, was a lot harder to update because you had to keep track of all these accesses and you were updating it much more frequently. And the other problem with it is just because you use that file 100,000 times yesterday doesn't mean you're going to use it today. Maybe there's a new version of that file and you're using this other one and its hit counter's coming up, but until it actually gets used more than the old one, it's not going to necessarily make it into the cache. So even if we haven't accessed this file for a week, because we used it a lot last week, it stays in the cache, possibly reducing the efficiency of our cache. And so it can accumulate a bunch of data that you're no longer using just because you used it a lot in the past. So we have these two different algorithms, and they both have pros and cons, but neither one is necessarily going to give us the best result. So in 2003, they came up with the adaptive replacement cache. And the idea is to have both. You know, if this cache is good for some stuff and this one's good for other workloads, why not just have both? So we start with a cache of size C, and we split it in half. And we'll do half of it as frequently used and half of it as recently used. And then, by keeping track of which one is working better, we move the partition in the middle to one side or the other, growing or shrinking the cache. So growing the cache that's working the best, that's providing the best performance for us. Then it also keeps a secondary cache of each of these two caches of the items as we push them out. So when an item was in the cache and we decided to get rid of it, to overwrite it with something else, we instead move it to this ghost list. We don't keep the data, just the key for the cache. But we keep track of which files were in the cache recently for both of these two caches. So your arc starts out looking like this. You have the LRU, the least recently used files, or the most recently used files kept in ordered by how frequently or how recently they were accessed. And then we divide that by this value P. And then we have the LFU, which is the frequently used files. And C is the total size. So we end up with 4 lists, right? The LRU and the LRU ghost, which is things that we've taken out of the LRU, and then the LFU and the LFU ghost. So when we get a request for some data from the cache, if it's in one of those 2 caches, if it's in the red or the blue, then we've done the right thing. We got a cache hit, our data was fast, and we're very happy. And now we know, OK, that block has been used. It was in the cache already, so we must have used it before, and we keep using it more. So we'll decide if that was in the recently used cache, it's now been used many times, so we'll move it over to the frequently used cache. And we know that keeping frequently accessed files has resulted in the happy condition, so we'll decrement the value of P, making the frequently used cache a little bit bigger and the recently used cache a little bit smaller, because caching frequently used data has resulted in happy. If it makes you happy, do more of it. But if the page we asked for is not in either of the caches, then that's too bad, better luck next time. But we will still take that data that we just used and put it into the least recently used cache, because we've just used it. So there's a good chance we'll use it again. And if we keep using it, then it'll migrate over to the frequently used cache. And so these 2 caches are constantly battling each other to be the most efficient. And every time you win, you get to steal a little bit of space from the guy who lost. So when a page is requested and it's on one of those ghost lists, meaning it was in the cache, but we had to remove it because we were running low on space. But if we find a page and it was on the ghost list, that means if only that cache had been a little bit bigger, that page would have still been in the cache rather than having been evicted. And so when a file was in one of these 2 caches but got removed because because we needed more space, we keep it on the ghost list, and when we get a hit there, we know, again, that cache, if it had just been a little bit bigger, this would have been a hit instead of a miss. And so we grow that cache. So if the file was in the least recently used cache, but it fell out because some other files were used more recently, but then we do end up using it anyway, and we know that if only we had made that cache bigger, it would have been there, then we increase P, giving the LRU a little bit more space in hopes that next time that block will be in the cache rather than in the you just missed me list. And the same thing for the LFU. And so we just keep moving P back and forth 1 byte at a time based on which cache is either giving us the hit or would have given the hit if it was just a little bit bigger. And so by sliding this back and forth constantly, the system adapts to your workload. If you're using a small number of files a lot, then the frequently used cache will keep getting bigger. But if you're just using the data you just used, and then after data is an hour old, you never use it again, then we'll keep growing the recently used cache because it's providing us the better result. And so that is the main arc, and we just keep adjusting that p-value to get whichever one is giving us the best outcomes. But sometimes you can't have as much RAM as you would like to keep all of this stuff in cache and make your workload fast. Sometimes there's just only so many slots on the motherboard, or you only have so much money. So if you remember back to the beginning of the talk, we talked about this idea of tiered storage. Well, if RAM is fast, but it's smaller and more expensive, then what if we could make the cache bigger by having some of the slightly slower but much bigger storage of the next tier down? And so that's where you get the L2 arc, or level 2 arc. Since the arc is stored in memory, which is very fast, but you can only have so much of it, what we do is because the LRU, the release recently used, is basically an ordered list, and every time you get used, you move back to the top, The things at the bottom are the ones that are about to fall off. And what we do is, instead of dropping them out of the cache and having to go to the slow hard drive every time we want it, when you're getting near the end of the list, if you have one of these L2 ARC devices, ZFS will make a copy of that on that SSD or NVMe or NVDIMM or whatever device you're using as your L2 ARC. So anything in the bottom quarter of that list is now eligible to be written out to this secondary cache. And so when it falls out, instead of just dropping all the data, we keep just a pointer that says, hey, that data is over on this SSD now. And so we can end up extending the end of each of those lists onto this SSD. So it does have a cost. The main reason why you don't want to have only a small amount of memory and very large L2 ARC is because in order to know that data is on the SSD, we need this pointer in memory saying that that block is on the SSD. And that takes some memory. And so if you make the secondary cache too much bigger in orders of magnitude than the memory cache, you will stop caching things in memory in order to keep this giant list of what blocks are on the SSD. And since the memory is faster, you probably want some of the data to be cached in memory, the most used, and then just the second level stuff to be on the SSD. And then the other advantage to this is that, or to mitigate the problem of those scans that we talked about, like when you're doing a backup, because that least recently used list is still going to suffer from the scan problem where you're going to keep running blocks through it. We don't want to completely fill our SSD with every file off our file system every time we do a backup. So to limit that, we only copy data out of the cache into the second level cache at a limited rate. And the default is like 8 megabytes a second, which when that was invented seemed like a reasonable rate because SSDs were only tens of gigabytes, and you could only write them so many times before they wear out. Now, you probably want to amp that up a little bit if you're using it. But because we only copy a portion of the data as it's falling out of the cache, we limit the disadvantage of that scan concept by not constantly overwriting the SSD with stuff we're not going to use. We just take so many megabytes a second of stuff that's going to fall out of the cache and put it in the L2 ARC. So that all worked quite well, but we can do even better. So ZFS, as I mentioned, has transparent compression. So when you write data to the disk, you don't have to do anything, but ZFS is going to compress it to make it smaller. And then store that compressed version on disk, which will take less time to write and less time to read back. But up until 2006, the way it worked is when we read it off the disk, we'd decompress it, get back the original version, make sure it was right with the checksum, and then put it in the cache. But George Wilson, who works for a database virtualization appliance company, found that they had a problem. The customer's database was about 800 gigabytes, and the maximum amount of RAM they could stuff into the server was 768 gigabytes, which is still a lot of RAM. But it wasn't enough to keep the whole working set in memory anymore. But the data compressed about 4 to 1. So on disk, it took a lot less space than that. So what George did was make a small change to defer the decompression. So when we read the data off the disk, we store the compressed version in memory, in the cache. And then each time we need it, we'll decompress it and then provide it to userland. So now, instead of our cache holding the logical size of the data, 800 gigabytes or whatever, it can store the physical size of the data, which could be compressed anywhere from 12% better to hundreds of percent better, meaning that we can fit more data in the cache. There's a small penalty in that, if it's frequently used data, you're going to keep decompressing this data over and over. But the decompression algorithms are very fast. Like LZ4, depending on your hardware, can decompress somewhere between 2 and 10 gigabytes per second per core. And there is actually another little cache. The data management unit in ZFS has a small cache that's, I think, 1/32nd of the size of your ARC. And it will store frequently, like any data we just decompressed, we keep a copy of it there, So if you access a file many times a second, we'll have the uncompressed version in this smaller cache as well. And so with that, most users see somewhere between a 50 to 200% increase in the efficiency of their cache, especially because things like metadata from ZFS itself compresses really, really well. So it means we can keep more information about directories and files and just the output of stat, basically, on the files in this cache by just compressing it first, or not decompressing it until after. But in order to make sure that because you do something like, say, a backup every Sunday, and you're going to walk through your entire file system, you're going to collect a lot of this metadata. The backup is probably going to have to stat every single directory and every single file on the file system, or even just the weekly periodic job that updates the locate database is going to go and poke every file. And so ZFS has the ability to limit how much of the data we're going to cache will be metadata so that we actually make sure there's some cache for the data, not just the metadata. Part of the other problem is that if you're actively using the data, like if you're operating on this data, it can't evict that data. So it has to find something else to evict to keep the arc under size. And kind of belying that graph I showed earlier, where you see the size of the arc is C, that's not really a fixed size. That's just a target, and that target even can change. And so in ZFS, you have 3 main tunables for this: the minimum size and maximum size of the arc. And there's also a newer one called arc free target, which is how much free memory you would like your system to keep. And if the value is below that, ZFS will shrink its C value to give back some of the memory to the system so you can use it for other applications. And it turns out that the version of this ARC algorithm they implement in ZFS is slightly different than the original paper, because the original paper assumed that all your pages would be the same size. But in ZFS, we use records that can be anywhere between a 512-byte sector on a hard drive up to 16 megabytes. And so the algorithm had to change a little bit to deal with the fact that every page isn't just 4K. One of the comparisons we often hear when we talk about the idea of a compressed arc is comparing to systems, other operating systems like Linux and Dragonfly have, of this idea of swap cache or compressed memory, where when the system's running low on memory, we're going to take some of the not as active memory and try to compress it. But waiting to do that until the system is already low on memory puts you in a weaker position, because you need to allocate some memory for the compressor to do its job, and you have to basically copy the uncompressed version to a new location with the compressed version. And if you're already low on space, it's probably, and there's a lot of demand on the system, it's probably the worst possible time to do that. Whereas ZFS, what we're doing is pulling the already compressed version off the disk and just delaying the extra work of decompressing it until we need it, meaning we get the advantage all the time, not just when we're low on memory. And we don't exacerbate the problem when we're under load and low on memory. So the compressed arc is using compression to create more cache, or to make the cache you have consume less space, so that that free memory is available to other applications, or so that all of the available memory can be used for as efficient as possible cache. And the big advantage here is what you're doing with compressed arc is always decompressing blocks. And decompression takes a lot less memory and a lot less CPU time than compressing data. Right? We do the compression when we're writing and it's not under load. But with the compressed arc, the operation we're doing frequently is decompression, which is much cheaper and faster, versus with some kind of compressed memory, you're always doing compression under when you're in the least ideal situation is when you're going to do the hardest work. And that's kind of backwards of how we would optimally like it to be. So then at the end bit here, I have a little bit talking about how you can tune the ZFS cache best for different workloads. So for your kind of general purpose workload, to make ZFS interoperate with other applications, so if you don't have a file server where all it's doing is ZFS and nothing else, for more general purpose workloads, the default settings maybe aren't the best. So the first one is that one I mentioned, arc free target, which specifies, sadly, in the number of pages instead of number of bytes, where every one of the other tunables is in bytes. Mark said he was going to fix that for me, but we never got around to it. We'd have to rename the sysutl, and it'd be annoying anyway, but yeah. By setting that to some reasonable value, you can make sure ZFS will give up memory sooner if your system's low on free memory. So you make sure that you always have some amount free to be using for your web browser and your laptop or whatever. So setting that to possibly a little bit higher than the default will make sure that ZFS will give up space a little more easily. The other thing is the default for the maximum size of the arc is most of the memory in your whole system. And if you're using the system as something other than a dedicated file server, you probably want to lower that. Setting the max to something like 50% will keep ZFS from dominating the system, while at the same time letting it take advantage of as much of the memory you're not using as makes sense to accelerate the performance. Because ZFS is copy on write, it means it has to do a little bit more work in a lot of places, and that your data, if it's spread out over time, is going to be kind of scattered across the hard drive. And it can use the arc and prefetch to try to mitigate the fact that your data isn't necessarily as contiguous and is a bit more fragmented and scattered. It can make up for that by having cache and read ahead, but not if you don't give it any memory. But if you let it use all your memory, it will. And since there's a delay to give that memory back, you can end up, if you let it, it will run off with all your memory. So setting arcmax to about 50% and tuning your arc-free pages maybe a little bit higher than the default, just like 10 or 20% higher than the default, will make the experience of using ZFS on a laptop or desktop machine where you need to leave some of your RAM for the browser. Usually the browser would like all of it, but don't let it have all of it. So that's the general purpose stuff. If you're doing a dedicated file server, you probably don't want to change those. Let ZFS have as much of the memory as you can. And you might also increase the metadata cache. So I mentioned how, by default, on FreeBSD anyway, the arc will only use 25% of its space for metadata. It kind of wants to cache some data to give you the best performance. But if your file server is storing millions of files or something, and you have to do operations where you index that or go through it with rsync or anything like that on a frequent basis, increasing that cap to let more of it be used for metadata might improve performance. Especially if you're using it as like a backup server or something where you're constantly doing all these stat and compare operations and not necessarily actually reading the data and want the performance for that. So if you have many files, you want more data, or more metadata cache, because then directory scans and things like that will be faster. But if that's not what you're doing, then you probably don't want to tune it and let it use more of the cache for the data you're trying to use rather than the stat of a file over in the corner that you're probably not going to use. If you're doing block storage, like using iSCSI to back VMware, the most important thing is making sure you get the block size correct. Basically, just look at the block size of the file system you're going to put on top of that block volume and make it match. Because otherwise, you'll end up with a situation where the default is 128 kilobytes. If your file system updates in 8 or 16 kilobyte chunks, you're going to have to read the whole 128K, change the middle 16K, and then write the whole 128K out again, which wears out your SSDs faster if you're using SSDs or whatever. But even just that, you've now multiplied the amount of work you're doing by 4 or 8 times as much work. And that'll hurt your overall throughput. And especially if it's a spinning hard drive, it only has so many IOPS. So if you can keep the number it's doing down, it'll be better. it'll leave more of them for you to do useful work. Now to touch on a bit of what Benedict talked about in his talk yesterday, is there are two different schools of thought on how to tune ZFS for a database. The first and original school of thought, especially before the concept of the compressed arc, was you actually want to make the arc small and tell the data set where you're putting the database to only cache the metadata, not the data, because you're going to have your database server use its buffer cache to cache the data that's in the database. Because the database actually understands which rows are actually still used, whereas when it's on disk, if you delete some data in the middle of a database, it doesn't actually free that space in the middle, it just marks it as unused or whatever. And so ZFS can end up caching a bunch of empty rows that you're never actually going to access. But you have accessed before, so they were in the frequently used cache or whatever. So oftentimes, your database server's buffer cache will have better knowledge of the data and how you're using it, and can make a better decision about which to cache. But because of the compressed arc feature, on Benedict's Oracle database, you saw he got over 8-to-1 compression. Well, it turns out letting ZFS do some of the caching when it can cache 65 gigs of data in 8 gigs of memory means it's actually going to cache the entire database, or the entire working set of it anyway, and give you a better result than the buffer cache in the database engine itself. So depending on your workload, you might decide to have ZFS not cache it and let the database handle it, or if you have very compressible data, it might work better to actually shrink the buffer cache in the database to be small and let ZFS handle caching it, because it'll do a cache of the compressed versions. But you never want to do both, because then you'll cache the block in both the ARC and the database, and use twice as much memory for each block of data, and that won't be useful. And yeah, so if you get very high compression ratios on your database, it might be better to let the caching be done by ZFS than the database. And then hypervisors, especially if you're running Beehive on FreeBSD, you want to make sure you shrink the arc so that Beehive actually has some memory that ZFS isn't constantly trying to steal, so that you can have decent performance. Seeing people try to oversubscribe the memory in their system, running too many Beehive VMs without taking some of the memory away from ZFS, and then the system's moving everything that's not a VM or ZFS out to swap, and makes your laptop feel really slow. So don't make the VMs fight with the ARC for memory. But again, you also have to consider what you're running inside of the VM to avoid double caching. If you're going to be running FreeBSD inside the VM, and it's going to have ZFS, it's going to have an ARC inside the VM. And so you want to disable caching on either the guest or the host so that you don't cache stuff twice. Even if you're using not ZFS in the VM, inside the VM, the OS has a buffer cache of some kind. And so it might make sense to disable caching on the data set in ZFS on the host and only let the guest do it in its own memory inside the VM. It depends, but if you are running the virtual machines on the machine with ZFS, you do want to consider what to do to avoid double caching everything, because the idea with the compressed arc is to get 2 or 3 times X the memory that you have as cache. But if you double cache stuff, you're getting less than 1-to-1 on your cache, and you're missing out on all the benefit. Sorry. Any questions? Colin.
So you mentioned with L2R, there's a limit on how quickly they will be pushed in there, and this has to do with not wanting to throw it out of SSD. If, say, hypothetically, you're using somebody else's SSDs, maybe some cloud provider that gives you local NVMe disks, and they don't care if you run them out, is there any reason to not raise this to some ridiculous amount of value?
So Colin's question was about the limited write rate of the L2 ARC. And if you're using someone else's SSDs, is there any reason not to just turn this up to 1 GB a second or whatever? And no, go right ahead. Burn up all of Amazon's SSDs. So there's actually two values. There's the write limit, and then there's another one, which also defaults to 8 megabytes, which is the write boost. So the boost sets how much more than the limit you will write if the the L2 arc has never been full yet. So because the L2 arc is erased every time you reboot because it relies on having the pointers in the RAM saying that the data is on the SSD, basically it will write to that SSD at double the speed, or the sum of the boost and the regular limit, until it's been full, and then it will only overwrite at the other rate. So you might want to tune both as well, especially if you're seeing worse performance when the machine first boots up and is still warming up.
You're saying that the L2 arc, you don't want that to be significantly larger than your RAM. Is there a reasonable rule of thumb for like either arc max or total memory size versus L2 arc size?
Yeah, I think the smaller L2 arc header is something like 100 bytes per block that you're going to have on the SSD. And so you can kind of figure out how much it's using, or even just by looking at the arc stats that you're going to get while you're using it, you'll be able to see. But in general, you just, you don't want to have 16 gigs of RAM and 5 terabytes of L2 arc. The idea of L2 arc is mostly when you can't get even more RAM, basically. But yeah, try not to go more than like 100x or something, or you're going to spend all of your RAM on pointing to the L2 arc and miss out on having even faster cache hits on the really frequently used stuff. Yes, so starting with FreeBSD 11.1, the arc max can be tuned without rebooting now. And I think almost all of the ZFS tunables are now runtime tunable rather than requiring a reboot on modern versions of FreeBSD, which helps a lot. Okay. Yeah. Again, like if you're using a ZVol to back VM, you might, again, so there's two properties for every data set: the primary cache, which is the arc, and the secondary cache, which is the L2 arc. So you can also configure certain data sets not to use the second level cache. Don't flush these blocks out to the SSD because I either need them very fast or I don't need them at all. I don't need the middle ground. Or you can say certain blocks will only go the other way. Colin again? No, but that would be interesting. Dan.
One of the nice things about Microsoft SP and MSDN stuff is that you get into your but all their images at present are UFS based. You don't have out of the box ZFS.
So making out-of-the-box ZFS instances for Azure. Steve has been learning a lot about that the last couple days. So, yeah. Yeah, I know. I would like to put a bit more of the image creation stuff that we have in make release into Poudrere as part of the Poudrere image command, and be able to have a very short one-line recipe to say, make me a FreeBSD 12.1 VHD that's ZFS en route, and so on. Because the nice thing with doing it with Poudrere is you don't actually have to compile all of FreeBSD. You can say, make me a jail by downloading the tarballs, and then now make me a VHD image of it. And you can get stock FreeBSD, set up whatever disk layout you want, and ready to go. So hopefully we'll have much easier ways of creating these kinds of images for everything pretty soon. So the question was about if any of the tuning parameters will go away as part of the changeover to the new OpenZFS port. I don't think so. We'd gain a couple more. And one of the really nice gains we get from the new OpenZFS port is the zpool iostat command that can tell you about your disk. Also has latency metrics now as well. And there's a couple other things. It also keeps histogram data, kind of, so you can get a short history of what it's been looking like rather than just what it's doing now. But most of the tunables are the same. If any disappear, it'll likely be by mistake, and just yell and we'll hook them back up. But yeah, the plan is to compare the lists. I think one or two might change slightly just because of changes upstream. But in general, no, we shouldn't lose any of the tunables.
If caching is concerned between the host and the VM that's running on that host, are there any similar parallel concerns for running in jail? Are there any sort of speed parameters that have problems with?
So the question was about double caching with jails. Because jails are using the host kernel, ZFS can actually, to ZFS, that's just a file in a directory, and so the host controls all the caching. Currently, there's no way for you to actually set limits to say, this jail can only use so much cache or something like that. But it might be interesting to do in the future. But it uses the one coherent cache for a jail, so you won't end up with any double caching. But yeah, it'd be nice if you could have some controls over what a jail could use. Because one of the other interesting things you can do with ZFS is actually delegate a data set into a jail by setting the jailed property on and jailing it. When you do that, root in that jail now has the ability to create their own snapshots, make child data sets, control the mount points. They basically get full control over that data set and all of its children. So you can actually make it look like they have their own pool. But it's just that one data set and all its children now can only be accessed in the jail. And jail controls the mount point, and they can do whatever they want, but not affect the host system. Okay. If you'd like to learn more, question to say. If you'd like to learn more, Michael Lucas and I wrote 2 books, ZFS Mastery, or FreeBSD Mastery, ZFS, and Advanced ZFS, and you can get them in the hallway. And Benedict and I do a podcast every week called BSD Now, where we answer usually between 1 and 3 ZFS questions as part of the show every week. And if you'd like to learn more about the ARC and a bit more of the original paper from 2003 and so on, there's a great talk from the Papers We Love conference called ARC After Dark. Yes.
Are there any implications if your L2 ARC is on the same storage tier as the main pool? Does not go with that one? If you're making data replication and you want to get other calls.
Right. So the question is about, is there any point in having an L2 ARC if your pool is all SSDs? And the answer is probably not, because if you're going to read the data from that same SSD, if it's not in the cache, then writing a second copy of it to the SSD is most likely just going to make that SSD slower because it's doing work, and more likely to make it worse than better. So yeah, an L2 ARC or a slog on the same SSDs as your pool data is not going to help because it's going to be the same speed as doing it directly on the disk as if it was part of the storage. Because with the slog, normally that's just part of the pool and gets written there anyway. And so having a separate one, if it's not actually separate, won't provide any value, and in fact might make it slightly worse. All right, thank you.